Welcome to the MOOCs course Advanced Thermodynamics. The title of the lecture is Intermolecular Forces and Non-Ideal Behavior. So, we will be discussing both about the intermolecular forces and then how they are going to show or display a kind of or induce a kind of a non-ideality in the system. That is what we are going to see. So, but before going into the intermolecular forces, we will be discussing a few basic important things about the ideal gas behavior, and then what are the forces in general act in the molecular level, those kind of things we are going to discuss before going into the details of intermolecular forces. In general, we know that intensive properties that can be experimentally measured are pressure, temperature, molar volume and composition. Let us say if you have a pure system, out of these four, the composition will not come into the picture, and then since 3 intensive variables should be there in a pure system, maximum one can have 2 intensive variables as a kind of independent variables. Okay. Now, constitutive equations relating these measurable variables by fitting experimental data is in general known as equation of state, and these equations of state are represented as function of temperature, pressure and volume. They can be presented in different form. Then P is function of temperature and molar volume, then molar volume is equals to function of temperature and pressure. And then in terms of dimensionless compressibility factor also, these equations of state are represented, that is Z is equals to PV by RT, and then that again can be function of temperature and molar volume or temperature and pressure. Okay. Now, we see equation of state for an ideal gas. For an ideal gas, we already know that equation of state is nothing but PV is equals to RT. That means compressibility factor PV by RT is equals to 1. Okay. So, ideal gas behavior in the sense the molecules occupy very small volume, negligible volume, and they are far from each other. They do not exert any kind of intermolecular forces. There is no force between these two molecules, any two molecules that you take, or any between molecules of ideal gas, there is no forces acting, right. That means, let us say if you have a kind of pictorially, if you graphically, if you wanted to represent, let us say you have a intermolecular forces or intermolecular potential, let us say gamma versus R, the distance between the molecules if you take, it is always 0. That is this horizontal line whatever is there, that is the graph. Pictorially, that is how we can represent. Okay. This point is gamma is equals to 0. Okay. So, that means if you have a non-ideality system, there is a kind of intermolecular force. So, how these intermolecular forces can be divided and evaluated, those kind of things we have to see. But we will see a few details of ideal gas, though we already know all of them. This equation of state for ideal gas is directly derived from kinetic theory of gases and valid for gas containing of molecules that are infinitesimally small, hard round spheres, but occupy negligible volume, exert forces upon each other only through collisions, exert no intermolecular forces. Right. And in the absence of intermolecular forces, that internal energy is independent of pressure and function of temperature only. That is the reason the molecular kinetic energy of molecules, that we can say that function of temperature. So, in this case we have only molecular kinetic energy, we do not have a molecular potential energy, because potential energy comes between because of the relative distance between the molecules, and then that relative distance when these molecules come close to each other, then this intermolecular potential develops. But in the case of ideal gases, there is no such kind of intermolecular force. So, then we have only molecular kinetic energy, and then obviously it is function of temperature only, it is not function of pressure. But as that is, in other words, as P tends to 0, all gases approach ideal gas behavior, because if there is no pressure, that means the only temperature is going to play role, and then with it increasing the temperature, molecular behavior is going to become more and more random, and then behavior the molecules are going to become, like the gas is going to become a kind of ideal gas. Okay. Then if intermolecular forces are included, what other kind of equations of state can arise, right. So, this what are these equations of state, okay, other than ideal gas behavior. When we include these intermolecular forces, then possible that we may have several equations of state that depends on the type of intermolecular forces. Several different types of forces may be acting. In some case one type of force may be dominant, in other case other type of force may be dominant. So, we cannot have a kind of one general kind of equation of state for non-ideal system like we have for ideal systems. Okay. For depending on system to system, there we may have a number of equations of state for non-ideal systems. But however, before answering these questions, what kind of other equations of states can arise because of these intermolecular forces, it is very much essential to understand what are these intermolecular forces first. Okay. So, intermolecular forces, there are many different types of intermolecular forces in general, but we will be discussing only which are relevant to the present topic of non-ideal systems. So, which include internal molecular energy, attractive forces, intermolecular potential functions and repulsive forces. Okay. We are going to see a few details of each of these types of forces. Let us start with the internal energy or internal molecular energy. We know that internal molecular energy can be divided into two. One is the molecular kinetic energy. Okay. So, because of translational, rotational and vibrational motion of molecules, this molecular kinetic energy exists, because these molecules, what happens, these molecules, even in the when there are no external forces are existing, sometimes what happens, these translate. They may be translating from one position to other position, they may be rotating, they may be vibrating as well. So, because of such kind of translational or rotational or a kind of vibrational kind of motion of these molecules, we can have a kind of molecular kinetic energy. Please be careful, these kinetic energy are the molecular kinetic energy, that is the kinetic energy associated with the molecules at the at molecular transport level only. Okay. They are not because of the bulk motions, and it manifests itself by velocities of molecules and is directly related to the measurable property temperature according to Maxwell-Boltzmann equation or Maxwell-Boltzmann statistics. Okay. So, that is kinetic energy is function of temperature directly, and another one is the molecular potential energy. Other one is the molecular potential energy. It is also associated with the relative motion between the molecules. So, at the molecular level, results from position of one molecule relative to the others in the system. This also referred to as intermolecular potential. Right. When the molecules, let us say in ideal gas system, molecules are far away from each other like this, right. But when you increase the pressure, these molecules obviously will come to close to each other, and then when they come close to each other, because of the relative position, intermolecular potential will be developed. Since this intermolecular potential energy depends on position, it can be readily related to measurable variable pressure. Obviously, when the molecules are far away, one is here, another one is here, when you pressurize them, it is obviously that they may come close. So, they are coming closer because of the pressurizing system. So, that is the reason this intermolecular potentials depends on position, it can be directly related to measurable variables. And then we now understand the non-ideality in the system is because of the intermolecular potentials, intermolecular forces, those intermolecular forces causing because of the intermolecular potentials, right. So, these are dependent on the directly related to the pressure of the system, okay. Pressure of the system. That is the reason the Figasti calculations, I repeat, the generalized expressions for the Figasti coefficient or Figasti of pure component I, etc., those we have derived at constant temperature and composition. If you remember in the previous lecture, whatever the derivations we have done, right. So, because pressure we cannot take constant if you wanted to bring into the system the effect of non-ideality, or if you wanted to establish the non-ideality due to the measurable variables, and then measurable variable is nothing but pressure in the case of molecular potential energy. So, there are no intermolecular forces in the case of ideal gases obviously. Thus, the position of molecules relative to others does not matter. Internal energy of ideal gas is independent of pressure and depends only on temperature, as we have already seen, but at constant temperature, as the pressure increases, the average distance between the molecules gradually decrease. If you increase pressure more and more, they may come very much close to each other, and then obviously when the average distance between these molecules decreases, then what happens, the molecules start experience the intermolecular forces. Okay. Thus their relative positions, when you increase the pressure, their positions relative to others get closer. Role of intermolecular forces start becoming predominant with increasing the pressure, and then thus it induces non-ideality in the system. Okay. So, pressure is the one, or increasing pressure or going pressure beyond P tends to 0, larger the pressure, you go to the larger pressure side, or gradually increase pressure, gradually this non-ideal behavior gradually increases. Okay. If you decrease the pressure and go towards P tends to 0, gradually non-ideality decreases, and then you eventually end up to coming to ideal gas behavior, where molecules are free from each other, there is no intermolecular collision, intermolecular potential, etc. Thus, it is important to develop more general equations of states by including intermolecular forces. Okay. Now, for developing more realistic equations of state by including intermolecular forces, what it is required? It is required to establish functional relationship for internal energy of the system as function of distance between two molecules and their orientations also. When you increase the pressure, what happens? The molecules may be coming closer to each other, and then there is a kind of relative orientation. These molecules also translate, rotates, and then vibrate. So, they may be moving here and there, different orientations may be there. Let us say one molecule is here, another molecule is initially here. So, it may go like this, it may come like this, it may come like this, and then it may go like this, any orientations it may take. So, then orientation also important factor along with the relative distance between the molecules for which we are trying to establish the intermolecular forces. So, that is one we have to understand. What is the functional relationship for internal energy of the system as function of relative distance between the molecules as well as their orientation as well. So, now there may be n number of orientations are possible, n number of relative distances are possible, within which there is a kind of intermolecular force. Obviously, there is a range, like in this certain range there may be intermolecular potential. After that, if the molecules go further away, then gradually intermolecular forces gradually decreases, and then it becomes 0 some distance. After that distance, we are not worried about, but within the distance between the two molecules, there is intermolecular force, and then if you decrease this distance further, so what happens? It is the intermolecular forces increases. Further, if you decrease, it may further increase. Like that, it may be there, and then likewise, n number of orientations of these molecules are also possible. So, when you wanted to know the overall intermolecular potential for this for any kind of system, then what you have to do? You have to average over all possible orientation and all possible relative distance between two molecules for which there exists intermolecular potential. Further, you need to improve understanding of intermolecular potential, which contributes to the non-ideal system. So, what is this intermolecular potential? This is what topic of the day for us. Okay. Intermolecular interactions between species arise from electronic and quantum nature of atoms, and then we know when a molecule is in close enough proximity to another molecules, electrically charged structure of its atoms can lead to either attractive or repulsive forces. In general, if the molecules of same nature, similar molecules, then these are touching each other, there will be repulsive forces. But as you move away slightly, what happens? Gradually, this repulsive forces decreases, and at certain distance, what happens? There will be no repulsive force or no attractive force, but further if you increase, what happens, it will start attracting force. So, when they come close to each other, they repel each other, but when they start going from each other, after certain point they will try to attract each other. These kind of things will happen, and then if you further gradually go increase the distance between the molecules, attractive forces decreases, and then eventually at certain distance far away from this molecule, there will not be any intermolecular potential. So, we are going to see a few of the attractive forces, because we realize that attractive forces are very much essential, because they are acting in the long range, right. Repulsive forces are there only in the short range, that is when R is close to the 0, or when the molecules are touching to each other or slightly away from each other. For that range only these repulsive forces are there. But what happens, as the distance increases, the attractive forces developing, and these attractive forces are there initially, they increase and then gradually then decrease, but they are there for longer range. That is the reason attractive forces are much more essential in discussing these intermolecular potentials. So, that is the reason first we discuss about the attractive forces. Okay. So, what are the attractive forces? In general, electrostatic forces between point charges are permanent dipoles, induction forces and dispersion forces cause a kind of attractive forces between the molecules, right. So, since intermolecular interactions result from electronic nature of atoms, it becomes important to understand electric field. What is electric field? Electric field intensity is defined as force per unit charge exerted on positive test charge Q in the field, that is, it is related to negative gradient of molecular potential energy gamma by this expression. Electric field intensity E bar is nothing but force by positive test charge Q, that is that force is nothing but minus del gamma, that is gradient of intermolecular potential. This del gamma is nothing but gradient of molecular potential energy or intermolecular potential. Okay. So, now we introduce this gamma intermolecular potential, and then most of this lecture is going to establish what kind of this relations are existing for gamma depending on the nature of the molecules, etc. Those things we are going to see, because now we understand this gamma is the one causing a kind of non-ideality in the system, right, and then it is function of relative position between the molecules and orientation of those molecules. Okay. So, this gamma as function of relative position as well as the relative orientation of these molecules, those things we are going to see in detail, and then write a few expressions for this gamma for different types of molecules. If in r direction only orientation, if you take, if you take the relative position or the distance between two molecules in only r direction, then F is equals to minus d gamma by dr. Okay. We can understand that electric field E bar is now related to the intermolecular force F and intermolecular potential gamma. Okay. Negative of the potential energy, that is minus gamma r, is the work. What does it mean by whatever this minus gamma r is there, minus gamma function of r is there, that minus negative of gamma r, what it is, what does it indicate? It indicates the work that must be done to separate two molecules from the intermolecular separation distance r to infinity separation distance, because this gamma is active for that separation distance r, right. This r may be 0 to certain r, between this limit only this gamma is acting, that is intermolecular potential is there. But if you go beyond r and then go towards the r is equals to infinity, there will not be intermolecular force. So, when you take two molecules, there is a gamma, that is intermolecular potential is there. Okay. So, how much work should you how much work should be done in order to separate these molecules beyond r and to infinity distance, so that there should not be any gamma, that is what, there should not be any intermolecular forces. So, that work, this indicate that work, that much work must be done to separate two molecules from the intermolecular separation distance r to infinity separation. there is no direct quantitative relationship between molecular physics and classical thermodynamics except in very simple cases. But most of these details are evaluated or developed on the basis of molecular physics, and then this equation states also etc., or intermolecular potential that we are going to see, all of them are developed based on the molecular physics. They are not part of thermodynamics, to be frank. But thermodynamic properties are being affected by this non-ideality of the system. So, we have to understand why this non-ideality is coming into the picture. That is the reason, though these topics are more related to the molecular physics, we are discussing, so that to have a kind of understanding why the system behave as a kind of non-ideal system in the presence of intermolecular forces. Okay. So, then why should we study the molecular physics? Because to strengthen the intuition about non-ideal behavior and judge about what equation of state to be used for a given application for a given system. Okay. For that also we need to have some kind of basics about the molecular physics. Then to understand why some of the equations of state work better than the others. Like let us say we have taken van der Waals equations and Redlich-Kwong equation in in some of previous lecture, and then we developed Fugacity of component I expressions, generalized expressions we developed generalized Fugacity expression, and then for these van der Waals equations and Redlich-Kwong equation, what are the Fugacity expressions, are the Fugacity of component in the mixture, which is described by equation of state or Redlich-Kwong Redlich-Kwong equation. Those things we have seen, but when you take the experimental information, okay, experimentally you find out the Fugacity of a system, and then under same conditions you use these equations of state, Redlich-Kwong equation of state or van der Waals equation of state, and then using those generalized Fugacity expressions you obtain the Fugacities when these two equations of states are obeyed. So, which one is matching better with the experimental results? Possible that both may be matching better depending on the system, possible both may not be matching better, possible that one of them may be matching better, another may not be matching depending on the system. So, if you wanted to understand further which system which equation of state is going to work better without doing much experimental study or without going into much details of thermodynamics, how can you establish, how can you develop that understanding? That understanding you can develop through molecular physics. Let us say if you have a kind of a non-polar system, then what are the intermolecular potentials those are available for non-polar system, and then which equation of state has incorporated the information about non-polar system or the non-polar nature of the system. Then obviously, if you know that information, that equation of state which is having information about the non-polar nature, then that must be obviously giving better results. That kind of understanding you may be having, right. You may be gaining if you understand, if you have some kind of basics about the molecular physics, though it is not relevant to the main course of thermodynamics, advanced thermodynamics. Though it may not be directly related to the present course of thermodynamics of non-ideal systems. We are estimating thermodynamic properties and then finding out the phase equilibrium composition when the system obeys non-ideal behavior. But we need to understand these kind of basic understanding is required. Then further, to understand relation between molecular physics and then classical thermodynamics. Though there is no directly quantitative relationship except very few systems, it is possible to develop a relation between molecular physics and classical thermodynamics using the advanced computational techniques like molecular simulations, density functional theory, etc. These kind of computational techniques are available nowadays. So, using those techniques one can develop relation between molecular physics and then classical thermodynamics. For that reason also it is necessary to know a few details about the molecular physics. And then finally, this is most importantly actually develop mixing rules for how thermodynamic properties of a mixture depend on composition. We have already seen in one of the previous lecture this let us say van der Waals equation of state we have taken. So, there are constant A and B, right, and these constants are dependent on the composition. When we were finding out the fugacity of component 1 in a binary mixture. So, this A and B are required for the mixture. So, which were not available and in general not available for any binary mixture. These A and B constants are available only for a individual pure gases. These kind of mixing rules also we have seen. So, this actually if you wanted to develop, then also you need to know a few basics of molecular physics. Okay. So, now let us start discussing about the attractive forces. They can be grouped as electrostatic forces between point charges or between electric dipoles, and then induction forces, and then dispersion forces or London forces. So, we see each of them in detail, so that to understand how these are going to bring in some kind of intermolecular potential, and because of that one how the system is going to behave non-ideal, that we can understand. So, electrostatic forces, Coulomb's law we all of us know, but however we need to have a kind of information, and then these electrostatic forces are very much important, and then much stronger than any other kind of attractive forces that we are going to study in this lecture especially, right. So, how we are going to see by example also. Electrostatic phenomena arise from the forces that static or slowly moving electric charges that exert some kind of forces on to each other. And then if you consider two point charges Qi, Qj, Qi, Qj are the magnitudes of these point charges. So, we are not taking minus Q plus Q like that, okay. They are magnitude of point charges, and these are separated by a separation distance r. Then what is the force acting between them, that we can know through Coulomb's law, that is F is equals to Qi Qj divided by 4 pi epsilon naught r square. What we understand, it is inversely proportional to r square. Okay. So, this is one of the important thing to observe in the subsequent lecture also, whether the intermolecular potential, or if you write in terms of force, how it is related to the radial distance or the relative position between two molecules, or relative distance between two molecules, because we understand this intermolecular potential is function of relative position of the molecules as well as their orientation. Okay. Now, we are taking fixed charges Qi, Qj, that is the reason we are not taking any orientation in this Coulomb's law. Okay. Here F is force in Newton, Q is charge in Coulomb, R is separation distance in meter, epsilon naught is dielectric permittivity of vacuum and is given by 8.854 into 10 power minus 12 Coulomb square per joule meter. Okay. Thus, potential energy, if you wanted to know, we know that F is equals to minus d gamma by dr. That means gamma is integral of f of r dr with a negative sign. So, whatever this f of r that we had just now by Coulomb's law, that you substitute here and then integrate. Now, here in place of f of r, f function of r, substitute Qi Qj by 4 pi epsilon naught r square according to Coulomb's law. Then Fij function of r, we will get Qi Qj divided by 4 pi epsilon naught r plus a constant, right. And then we know this is again gamma ij, that is intermolecular potential. F is the force between two molecules, whether this gamma ij is the intermolecular potential energy between these two molecules, it is inversely proportional to r, okay. That is the separation distance, okay. And now we know it is inversely proportional. So, obviously, when we move away, these molecules move away from each other at infinite distance, there will not be any force acting amongst them, they will be independent of each other, there will not be any force or intermolecular potential between these two molecules. That means, at r tends to infinity, gamma tends to 0, that means constant is 0, that means finally between 2 point charges, the intermolecular potential gamma ij is nothing but Qi Qj by 4 pi epsilon naught r. For charged molecules, that is For ions Qi and Qj are integral multiple of unit charge E, and thus potential energy between two ions is nothing but gamma ij Zi Zj E square by 4 pi epsilon naught r, where Zi Zj are ionic valences, and then E is nothing but 1.60218 into 10 power minus 19 coulomb. Okay. So, from these expression we can understand how much it is significant intermolecular potential between point charges due to the electrostatic phenomena. Okay. So, we can much better understand the same thing by an example. We will do that one as well. So, for a medium other than vacuum, gamma Ij is equals to Zi Zj E square by 4 pi epsilon r, okay, where epsilon is the absolute permittivity defined as epsilon is equals to epsilon naught epsilon r. Epsilon naught we already know it as permittivity of vacuum, epsilon r is dimensionless dielectric constant or permittivity relative to that of vacuum, and it is 78.41 at 25 degree centigrade for water, whereas for vacuum it is nothing but equals to 1. So, that in the vacuum epsilon should become equals to epsilon naught. Now, we take an example and understand how significant or how much important are these electrostatic forces between two ions. Calculate potential energy between two isolated ions Na plus and Cl minus separated at a distance 2.76 angstroms. Okay. So, two ions are given, that is Zi, Zj are given. So, Zi is plus, Zj is equals to is minus 1. Okay. So, electronic valences are plus 1 and minus 1 for these two. Then we know this gamma ij is nothing but Zi Zj E square by 4 pi epsilon naught r. So, vacuum we are taking because nothing has been mentioned. So, Zi is minus 1, Zj is equals to plus 1, E is 1.60218 into 10 power minus 19, epsilon naught is 8.854 into 10 power minus 12, and then separation distance is 2.76 angstrom, that is 2.76 into 10 power minus 10 meters. When you substitute these numbers, then you will understand this gamma ij is nothing but minus 8.36 into 10 power minus 19 joules. So, this minus, as I already mentioned, the minus indicate attractive forces. So, what we understand, when these two Na plus and Cl minus ions are 2.76 angstroms distance apart from each other, there exists an attractive force between these two, and then magnitude of that attractive force is nothing but 8.36 into 10 power minus 19 joule. Okay. Now, this number we got, two things we got, the nature of the force, whether it is attractive or repulsive, that we understood. Another one thing, what is the magnitude of the force, that we understand. But we can understand much better about this one when we compare this one to the other kind of forces. Okay. Let us say thermal energy at room temperature, that is 300 Kelvin. If you calculate, it is nothing but kT, K is Boltzmann constant. So, that is 1.38 into 10 power minus 23, temperature is 300 Kelvin if you take roughly, then it comes out to be 0.0414 into 10 power minus 19 joule, right. So, now this order of 10 power 19 intentionally kept like this, so that we can understand. Now, we see here the electrostatic forces, the intermolecular potential due to the electrostatic behavior of these two ions is 8.36 into 10 power minus 19 joules of attractive force, whereas the thermal energy is only 0.0414 into 10 power minus 19 joules. So, that means such high magnitude of electrostatic forces are there. Okay. Thus, compared to other intermolecular energies such as thermal energy, the magnitude of Coulomb energy is larger, obviously magnitude wise we can see, and of large range. What does it mean by large range? At 2.76 angstroms, we have attractive force of 8.36 into 10 power minus 19 joule, right. But if you increase this distance gradually, what happens? This gradually decreases. But it decreases, but it still will be there for long distance. That is what mean by long range. How much long, that relative to thermal energy we can calculate. Let us say if you divide this Coulomb energy divided by the thermal energy and multiply by 2.76, whatever the distance is there. So, that distance approximately 560 angstroms you are getting. That means, when this Na plus Cl minus ions, when they are 2.76 angstroms distance only, that is very small distance between these two, right. So, there is a attractive force of 8.39 into 10 power minus 19 joules, but if you increase the distance, how much you increase? You increase to 560 angstroms, very large distance, but despite of this distance, there is a kind of intermolecular potential between these two, and that intermolecular potential is equal to thermal energy. So, that is what mean by long range. Okay. So, they are existing at longer separation distance, that is what it mean by. These electrostatic forces, now we can understand this Na plus and Cl minus, the attractive force is so strong, so high, because of that one in general we know that ionic molecules whatever are there are the salt like NaCl which dissociate as Na plus and Cl minus, their force, attractive force is so strong, and then it is there for the long range. Because of this reason, what happens melting of such salt requires very high energy. That is the reason melting point of these salts is very large. So, that is how we can understand how much significant is the force between two ions or two molecules, and then we can later on relate that one to the non-ideal systems. So, next one is the electrostatic force due to the electric dipoles. What happens when even when there is no net electric charge, then also it is possible that electrostatic forces may exist, right. So, that how does it happens, that is what we are going to say. We know in general, because consider a particle having two electric charges of same magnitude E magnitude, but opposite sign, that is one is having plus sign, another one is the minus sign, and are separated at a distance d apart from each other. Then such particle has an electric couple or permanent dipole moment mu defined as E multiplied by d. Dipole moment mu is given by E multiplied by d. So, how does it occur? Because when even though net charge is 0, there is no net charge, what happens, some kind of electric field is developed in some molecules, right. Because of that electric field, this dipole moment is developed. Okay. So, we will see that one. Strength of dipole is characterized by dipole moment mu, that is a vector that moves or points from negative sign to the or negative charge to the positive charge. Units of the dipole moment is dBi, and it is equal to 3.33569 into 10 power minus 30 Coulomb meter. Dipole moment of a pair of charges plus E and minus E separated by 0.1 nanometer is nothing but mu is equals to 1.60218 into 10 power minus 19 coulombs, that is E multiplied by 0.1 nanometer, that is 10 power minus 10 meters distance apart from each other. So, that comes out to be 1.60218 into 10 power minus 29 Coulomb meters, but 3.33569 into 10 power minus 30 Coulomb meter is 1 dBi. So, if you convert this one into the dBi, you will get 4.8 dBi, right. So, pictorially, let us say this is a negative charge here, we have a positive charge here. So, then because of some kind of arrangement, what we can say that there is a covalent bond is existing, sharing of electrons are taking place. So, then under such conditions, it is possible that one of the molecules may be more electronegative compared to the other one. So, because of that one, though the overall net charge is 0, there will be a kind of electric field. Because of that electric field, there will be a kind of a permanent dipole moment mu, and then that points from minus negative point to the positive plus point. right. Under such conditions electric fields, but obviously they should they are pointing from plus charge to minus charge. Okay. Now, the charges plus charge, one plus charge, one minus charge is balanced, but still there is a kind of a electric field is developed. Because of this developed electric field, what happens, permanent dipole moment may be there even for for the things where there is no net charge. Okay. We take an example and see. So, dipole moment realization at molecular level is obviously required, because when sharing of electrons in a covalent bond is unequal, an atom can gain electron density at expense of the atom to which it is bonded. For example, if you take HCl molecule with Lewis dot structure as shown here. So, these dot are shown for the valence electron of Cl, and then cross is shown for the valence electron of the H. Now, the chlorine is more electronegative. We can see 7 electrons are there in valence. It needs only 1 electron to fulfill or complete the valence electrons and become stable, right. Whereas, the hydrogen also it is having only 1 electron. If it can get 1 more electron, its outer shell will valence would be fulfilled with the 2 electrons nearest one. So, that can also be stable. So, then what they do, they share electron each other, but this Cl minus is having, it is more electronegative. So, what happens, it pulls the electron of hydrogen towards it more strongly than hydrogen pulls the electron of chlorine towards it. Okay. So, there is a imbalance, though they are sharing, they are being shared unequally. Because of this unequal sharing, a kind of a charge will be developed. Because of that one, electric field will be developed. Bond is formed by sharing of 1 electron from each molecule. However, chlorine is highly electronegative since it needs an electron to complete its outer shell. Thus, it pulls electron from H much more strongly than H pulls electron from Cl. In other words, electrons are not shared equally. Rather, lone hydrogen electron spends more time close to the Cl atom than the shared Cl electron does next to H atom, right. Because of this one, what happens, this results net charge separation with chlorine obtaining a net negative charge and hydrogen obtaining a net positive charge, and this separation of charge leads to permanent dipole moment. And then for HCl, magnitude of dipole moment is nothing but 1.08 d. If you know the bond length or the separation distance between this H plus and Cl minus, then you multiply by E. So, then you will get 1.08 d by. Okay. So, diatomic molecules with electronegative like fluorine, chlorine, etc., or electropositive such as lithium, sodium, etc., atoms have large dipole moments in general. Diatomic molecules with dissimilar atoms such as HCl, H and Cl are dissimilar each other, will always exhibit some degree of charge separation. However, it may be small. Thus, these molecules will have permanent dipoles, and then pictorially if you see for H and Cl minus, we can see H is smaller and Cl is a bigger one, and then Cl is more electronegative than the H. So, because of that one, the electric field is developed, and then that electric field induced the dipole moment, and that dipole moment may be causing some amount of non-linearity or non-ideality in the system. Further, polyatomic molecules with more than 2 atoms, it is required to check the molecular structure to see whether a dipole is existing or not. So, it is difficult to say for polyatomic molecules directly like this. Let us say HCl, only 2 molecules are there, we can see their electron valence electrons, etc., and then we can understand what kind of charge is going to develop, whether the charge is or the electric field is going to develop or not, because of which is there any dipole moment going to exist or not, that we can understand. But if more than 2 molecules are there, it is difficult to say directly, and one has to see the molecular structure and then understand. So, dipole moments are caused by non-symmetric distribution of electron cloud in the molecule, that is what we understand. So, thus symmetric molecules does not have any dipole moment, because whatever the non-equivalent sharing of electron cloud is there, that is because of the non-symmetric distribution, okay, that is non-symmetric molecules, because of that one is there. So, obviously that means symmetric molecules will not have any kind of a dipole moment. Greater the asymmetry, greater the dipole moment. For example, electron cloud CH3Cl is pulled strongly to electronegative Cl and exhibits a dipole of 1.87 dBi. Okay. So, a few more examples of molecules having dipole moment along with the magnitude of dipole moment are given here. In the parenthesis, magnitude of dipole moment is given, how much is the dipole moment. A few examples of molecules having zero dipole moment, that is which are not having any dipole moment, they are also given here. Now, interaction of one dipole with a neighboring dipole is known as a dipole-dipole interaction. It is and such interactions also lead to deviation from ideal gas behavior. So, two charges, one is positive charge and another one is negative charges, though balance net, that is they are balancing each other, there is no net charge, but despite of that one there is a electric field. So, there is a dipole moment between two charges, okay, of opposite sign. So, there is a one dipole, like that there may be another dipole. So, there may be interaction between two different dipoles, and then that because of that interaction between dipoles, whatever the force is there, intermolecular force is there, that is known as the dipole-dipole interaction, and then that also induces some kind of a non-ideality in the system or deviation from the ideal gas behavior. Potential energy of two permanent dipoles I and J is obtained by considering Coulombic forces between four charges. Potential energy of such interactions depend obviously on the distance between dipole centers and on relative orientations of dipoles. Exactly similar way like electrostatic forces between 2-point charges, here also it depends between the relative distance between the center of two dipoles and then relative orientation of dipoles. If wanted to relate this type of electrostatic force to macroscopic behavior, one must average over all possible orientations. Okay. So, let us say we have one negative charge here, another positive charge is here. So, the balance is 0, there is no net charge, right. They are a separation distance di from each other, okay, and there exists a kind of a dipole moment, let us say mu I. Similarly, there is a positive charge here and there is a negative charge here, okay. They are a distance dj apart from each other, okay. Obviously, between these two charges there is a dipole moment mu j, okay. These dipoles, let us say either ends of these two charges are there. So, they may be orientating different orientation, any different possible orientations are possible, right. Even sometimes distance also may change, but let us take a distance dj constant. So, these orientations are there. So, these orientations, let us say if you take this is the horizontal line. So, one orientation, let us say if you take theta I for a first dipole moment mu I. Similarly, other dipole mu j, the one orientation angle you take theta j, like that several theta I and theta j's are possible, and then you align them along one straight line like this. So, at this end one dipole moment, at this another dipole moment is there. So, this dipole moment may be rotating here and there and then like this or like this, different orientations are possible. So, there is a angle between this dipole this horizontal line and then orientation of dipole, this particular dipole, like that other dipole also different orientations are there. So, these angles let us say phi phi j, how they are rotating along the same horizontal line. So, like this few orientations are taken, and then you can obtain the dipole-dipole interaction for each orientation and then each rotational angle, etc. And then you can do such kind of calculation for all possible orientations, and then you can do a kind of average. So, free rotation of a dipole, let us say if I show with charge, it can be like this as well. So, now if dipole separation distance r, so these two dipoles whatever the mu I mu j are there, dipole moments mu I mu j are there. So, they are separated by distance r, and this r is larger than d I or d j, then the average potential whatever the potential is there, that for this orientation shown here, the intermolecular potential gamma I j, we can write it as minus mu I mu j divided by 4 pi epsilon naught r cube multiplied by 2 cos theta j minus sin theta j cos phi I minus phi j. This is what we have. Okay. So, these things actually we are not deriving because they are derived in they are of important from a molecular physics course point of view, but that is not primary aim of this course. So, that we are not deriving all these kind of derivations, we are just adopting them. If dipoles are in the same straight line and charges of two dipoles facing each other, let us say here in the orientations are different orientations are shown. Okay. They are aligned in the same straight line, but different orientations, angles, etc. are shown. But when they are aligned in the same line, but their same charges like negative charges, similar charges, here negative, they are facing each other, then the potential whatever is there, that is going to be largest one. Okay. But if these charges, opposite charges, they are still in the same aligned in the same straight line, but that opposite charges here plus here minus are facing each other, then whatever this potential is there, that is going to be lowest one. That one can get from this expression anyway by appropriately taking what is the theta I theta j. So, in an assembly of polar molecules, relative orientation of these molecules depend on the interplay of two factors. What are these factors? First one is the electric field set up by polar molecules tends to line up the dipoles, whereas the kinetic or thermal energy of molecules is the other one, which tends to toss them about in a random manner. So, that means if you increase the temperature, what happens? These orientations become more and more random until in the limit of very high temperature, the average potential energy due to polarity becomes vanishingly small. So, that is the reason we say that at high temperature usually we may not have any kind of intermolecular potentials, and then system behaves as a kind of ideal gas, that is at very high temperatures, and it is experimentally proved as well. But at low and moderate temperatures, behavior of polar gases is remarkably different from that of non-polar gases. Okay. And this difference tends to disappear as temperature increases. So, let us say whatever the dipole moment for the polar molecules that we have seen, though the net charge is 0, net charge is 0, there is a kind of electric field developed because of the imbalance or unequal sharing of the electrons, right, and then because of that one there is a dipole moment is existing, and if the dipole moment is existing, then we can say those molecules as a kind of polar molecules. If they are not existing, then we can say non-polar molecules. Average potential energy between two dipoles in a vacuum at fixed separation r can be found by averaging all orientation with each orientation weighted according to its Boltzmann factor, and let us say for dipole-dipole interaction it is given by gamma I j bar is equals to minus 2 by 3 mu I square mu j square divided by 4 pi epsilon naught whole square k t r power 6 and so on. So, this is a series in terms of expanded in power of k t, but we are taking only 1 k t power, we are taking only first term only. Okay. So, according to this equation, for pure substance, pure polar substance, that is if I is equals to j, then potential energy what happens? It becomes like mu I power 4, that is potential energy varies as 4th power of dipole moment if I is equals to j. So, it indicates a small change in dipole moment can produce a large change in potential energy due to permanent dipole forces. This indicates how much important to consider this permanent dipole moments while calculating intermolecular potentials of a given system. Okay. On the other hand, contribution of polar forces to the potential energy is small for molecules having dipole moment of 1 dB or less. Otherwise, this contribution becomes increasingly significant for small molecules having larger dipole moments. Since as the way that we have a dipole moment between 2 point charges, though there is a kind of net charge is 0. So, it is also possible to have a kind of quadrupole moment, that is between 4 charges, though the net charge is 0. It is possible to have a quadrupole moment due to concentration of electric charge at 4 separate points in the molecules. Let us say dipole moment plus minus charges are aligned like this in general. It can be other way also, orientations I am not showing, or it can be like this. So, if you turn one of them to 180 degrees, then you will get the other dipole here. Okay, the orientation plus minus, minus plus, it will become other way around. Okay. So, likewise, if you have a quadrupole like this, minus plus, plus minus, or plus minus minus plus like this, you cannot get the other one by whatever the degree you rotate it. Okay. So, when you have such kind of charges, four charges at 4 separate points in the molecule, then also it is possible to have a quadrupole moment. For example, CO2 does not have any dipole moment, but its quadrupole moment is sufficiently strong to affect its thermodynamic properties that are different from those of other nonpolar molecules of similar size and molecular weight. For the simplest case of linear molecule, quadrupole moment Q is defined by sum of second moments of the charge as Q is equals to sigma EI dI square, where the charge EI is located at a point, a distance dI away from some arbitrary origin where all charges are on the same straight line. Okay. So, the potential energy between a quadrupole and a dipole or between quadrupole and another quadrupole is function of obviously separation distance and angles of mutual orientation here also. Average potential found by averaging over all orientations, each orientation is weighted according to Boltzmann factor kT. Then for one dipole I and then one quadrupole J, the average potential energy gamma ij bar, bar indicates average, is nothing but minus mu I square qj square divided by 4 pi epsilon naught whole square kT r power 8. Here we can say it is r power 8, inversely proportional to r power 8. If we have one quadrupole I and another quadrupole J, then average potential energy because of the interaction between these two quadrupoles I and J is gamma ij bar, that is minus 7 by 40 qi square qj square divided by 4 pi epsilon naught whole square kT r power 10. Here you can see it is r power 10, inversely proportional to r power 10. Okay. R is the separation distance. Experimental and theoretical information on dipole moment is very extensive, but very less is known about the quadrupole moments, and even little work has been done on higher multipoles. Effect of quadrupole moments on thermodynamic properties is much less than that of dipole moments, and the effect of higher multipoles is usually negligible. Intermolecular forces due to multipoles are of extremely short range than dipoles. That means whatever the intermolecular forces are there because of the quadrupole or higher multipoles, what happens, they exist only for small distance. If the molecules go slightly away from each other, they become very small that they can be negligible. They can be neglected without any difficulty. So, in the subsequent lecture, what we will be discussing? We will be discussing other types of attractive forces such as induction forces and then dispersion forces. The references for this lecture are given here: Engineering and Chemical Thermodynamics by Koretsky, Molecular Thermodynamics of Fluid Phase Equilibria by Prosnit et al. Chemical, Biochemical and Engineering Thermodynamics by Sandler. Introduction to Chemical Engineering Thermodynamics by Smith et al. So, most of the details presented in this lecture are taken from these two books, that is Prosnit et al. And Koretsky. Thank you.